To make the previous solution can fulfill the bounded waiting requirement, we need to do a modification based on the previous solution. So remember, in the previous solution, after the process exit the critical section, the process will directly release the lock so that other processes can grab the lock and access the critical section. However, the main idea of the modified solution is different from the previous one. So instead of directly release the lock, the current process will check whether there is a process who is waiting for the lock. If yes, the current process will directly pass the lock to the waiting process, so that the waiting process can directly get the lock and access the critical section to avoid the problem which we illustrated in the previous slides. While the process is waiting, so other process can access the critical section before it, which causing the bounded waiting requirement cannot be fulfilled. But if the answer is no, the current process will release the lock. To achieve this, so surely we need other variables. For example, we use a global variable waiting array to help us record that whether the process indexed at I is waiting or not. For illustration purpose, we use two processes, P0 and P1, for demonstration. So where index I in process P0 is equal to 0, and the index I in process P1 is equal to 1. And also, lock is initialed with false. Both waiting 0 and waiting 1 are initialed as false as well. Assuming P0 is put on the CPU first. So inside the do-while loop, both waiting 0 and key are changed to true. Then check the condition for the next while loop. Since both waiting 0 and key are true, test and set function will be called. The old value of lock, which is false, is assigned into key, then assign new value true to lock. Then do the while loop again. So since key is false now, so we will out of the while loop. Then change the waiting 0 to false. Because P0 is on the CPU now and ready to access the critical section. Then P0 access the critical section after that. So let's assume the worst situation happened. So P0 is taken out of the CPU by the interruption. Then P1 is put on the CPU to execute. So waiting 1 and the key are set to true, then fall into the while loop. Test and set function is called. Then currently the old value of lock is true. Then key will be set to true as well, and the lock will be assigned a true value again. So since both waiting 1 and the key are true, process P1 will be stuck at the while loop until it is taken out of the CPU. Then P0 is put on the CPU again. So after P0 exit the critical section, so we use another temporary index J to denote the next waiting process. First, we initial J with I plus 1 mod N, which is the next process index right after I. So we use I plus 1 to mod N because we treat all the processes as a circular array, where N is the total number of processes. In this case, N equal to 2. Then J equals to I plus 1 mod N, which is equals to 1. So before P0 get into another while loop, it checks two conditions. One is whether J is equal to I. Another condition is to check whether process Pi or P1 is waiting or not. So in this case, we know P1 is waiting now. After we add the exclamation before waiting 1, it becomes false. Then P0 is directly out of the while loop. then we do another check to see if j is equal to I. If yes, means there's no other process is waiting there, so we can directly release the lock. But if no, means there's a process is waiting there, then we can directly pass the lock to this waiting process. So in this case, since j equal to 1, which is not equal to I, means process P1 is waiting there. So P0 directly pass lock to P1. Then keep executing the remainder section. Then assuming the worst situation happened, so P0 continually stacks into another round. Let's see whether P0 can access the critical section again or not. So P0 set both waiting 0 and the key to true, then fall into the while loop and can call the test and the set function. However, due to the old value of lock is true, so therefore P0 will be stuck at this while loop until interruption happen and move P0 out of the CPU. Then put P1 back. Then P1 continually run the while loop and call the test and set function. Assign true to key, then do the while loop again. So even though key is equal to true, waiting 1 is equal to false now. Then P1 will be out of the while loop and access the critical section. Until this point, you can see that so this modified solution can fulfill all the requirements for addressing the critical section problem. So you may further check if P1 can get another chance to access the critical section right after this round, while P0 is still waiting there through this pseudocode.